All right. Let's move on to 5.2. 5.2 is all about the indefinite integral. And so the idea is this. So a function capital F is called an antiderivative of lowercase f on a given open interval if capital F prime equals lowercase f for all x in that interval. So for example, an antiderivative of x squared is 1/3 x cubed, because the derivative of 1/3 x cubed is, well, it's 3 times 1/3 times x to the 3 minus 1, so it would just be x squared, right? Which is just the original function. But note that this antiderivative is not unique. 1/3 x cubed plus 2 would also be an antiderivative, since when you differentiate this function, you get x squared again. And 1/3 x cubed minus root 7 over 5 is also an antiderivative. In fact, if capital F is any antiderivative of lowercase f on an open interval, then so is capital F plus c, where c is a constant. Okay. Now, why are we interested in antiderivatives? Well, because, as you may recall from the previous section, if a of x is the area under f of x over the interval from a to x, then the derivative of that area function is equal to this original function f. In other words, the area function is an antiderivative of f of x. So if we can get really good at finding antiderivatives, then solving area problems is going to be really pretty easy. The process of finding antiderivatives is called antidifferentiation, or a much more common term is integration. Okay. Now, if capital F is an antiderivative of lowercase f, then we write this statement, right? This symbol is called the integral symbol, and in this case, lowercase f here would be called the integrand. Okay, so we would say the integral of lowercase f equals capital F, right, plus c. C is just called the constant of integration, and anytime you're doing indefinite integrals, you should always have a plus c in your answer. Okay. So a couple things to point out. First of all, we have a whole bunch of statements about antiderivatives, right? Antiderivatives that are equivalent to statements about derivatives that we already know. So, in other words, if the antiderivative of lowercase f is capital F, that's exactly equivalent to saying that the derivative of capital F is lowercase f, right? Those are exactly equivalent statements. Another thing that follows immediately from that is that the derivative of the integral of a function is just the original function, right? So if you integrate a function and then take the derivative of it, well, you just get the original function back, okay? So I wanted to draw your attention to page 260 of your textbook, because this is a really good table that summarizes all of the derivatives that we've talked about, right? So you have the power rule, you have the derivatives for all the trig functions, you have derivatives for exponential functions, logarithmic functions, inverse trig functions, right? So they're all there. And if you know these differentiation formulas, then you know their corresponding integration formulas. You just have to think backwards, okay? So what I want to do is practice thinking backwards. Practice finding antiderivatives. So let's do that. So let's evaluate some integrals. Let's do this for x cubed. Okay, so we're going to think backwards, right? Normally what you do, if you're differentiating, you would take this number down and then subtract 1 from the exponent. But here we're going to work backwards. So instead of subtracting 1 from the exponent, we're going to add 1 to the exponent, and then we're going to divide by that number, okay? So it's going to be, we're going to get x to the 3 plus 1 divided by 3 plus 1. and then don't forget your constant of integration. Anyway, that comes out to x to the 4th over 4 plus c. Now, you don't have to write out this middle step. In fact, I want you to get to the point where you can jump straight from here to here. I just wrote it out now because, I mean, this is the first time we're doing this, so I wanted you to see my reasoning. Okay? Let's do another one. See if you can pause the video and figure this one out on your own. Integral of 1 over x to the 5th. Okay, so here's my solution. Notice that 1 over x to the 5th is just the same as x to the negative 5. And then I can use the same trick as before, right? Add 1 to the exponent and then divide by that new exponent. Right, so that's just x to the negative 4 over negative 4. Or if you like, you can call that negative 1 over 4x to the 4th. Okay. Let's do one more kind of like this. See if you can figure out the integral of the square root of x. Okay, so square root of x is just x to the 1/2 power, right? And then I'm going to skip this little middle step, right? And I'm just going to say, well, if I add 1 to the exponent, then I get 3/2. And then, so I'm going to have x to the 3/2, and then I'm going to divide by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So I guess at the end of the day, what I really get is 2x to the 3/2 divided by 3 plus c. And that's that one. Okay, a couple of facts that will help us to evaluate slightly more complicated integrals, right? So the integral of a function, if you're multiplying a function by some constant c and you want to integrate that, you can actually take the constant out and then just integrate the function. So that's what part A is saying. And then part B is saying that we can distribute the integral across addition and subtraction, right? So we can distribute the integral. You cannot distribute the integral across multiplication and division. Okay, it doesn't work. But you can distribute it across the addition and subtraction, which is really nice. The proofs are really simple. Basically, if we differentiate the right-hand side, then we should get the integrand of the left-hand side. So if you just take this thing and differentiate, you should be able to show that it's the same thing as this. Okay, and that's all we're doing in both of these proofs. So I'm not going to necessarily walk you through them because they're straightforward. But what I do want to do is practice. So let's practice some more. Okay, so for example, the integral of 4 cosine x dx, we can take this constant out, right? We can call this 4 times the integral of cosine x dx. And that's a little bit easier for our brains to handle, I think. Antiderivative of cosine. Well, so I should think to myself, what the derivative of what function is cosine? And the answer would be sine, right? The derivative of sine is cosine. So the integral of cosine is sine. This is 4 sine x plus c. Okay, let's do x plus x squared. So go ahead and pause the video, see if you can figure that one out. Okay. So here we can distribute that integral, right? And for this first one, we've got an x to the first power. I add 1 to the exponent and then divide by the new exponent. Here I'm going to get x cubed over 3. And of course I've got my constant of integration that comes along for the ride. So that's that one. Here's another one for you. See if you can do 3x to the 6th minus 2x squared plus 7x plus 1. See if you can integrate that. Okay, so I'm not going to bother showing the distribution and all of that stuff. I know that I can kind of handle each one of these things independently, so I'm going to do that. So if I add 1 to the exponent and then divide by the exponent on this first term, I'm going to get x to the 7th over 7. I have to multiply by 3 though, so I'm going to have 3x to the 7th over 7. Here I'm going to have minus 2 times x cubed over 3. And here I'm going to have 7 times x squared over 2. And here, now if you think of this as like x to the 0 power, you add 1 to the exponent, you get x to the first power, and then divide by 1 and you just get, well, you just get x, right? So you get plus x, and then don't forget your constant of integration. Okay, so pretty cool. I want to show you, I have 5 more examples in total, but I want to show you 3 kind of problems like this that are maybe a little bit more complicated. So let's say that you were confronted with something like this, cosine x over sine squared x. Now you have a couple of challenges here. First of all, the integral does not distribute across division. Okay. Second of all, even if it did, you don't know what the integral of sine squared x is. So we have to try to manipulate this expression so that it looks like something we know how to, so that it looks like something that is the derivative of a function that we know, right? So there are lots of things you could do. I mean, one thing that occurs to me is that sine squared x is 1 minus cosine squared x, but then you're kind of stuck there too, right? There's not much you can do with that. But another thing that I think of is this. So I can split the sine so that I have cosine x over sine x times 1 over sine x. Okay? And cosine over sine is cotangent. 1 over sine is cosecant. So, is there a function whose derivative is cotangent x cosecant x? Or, to give you another hint, right, is there a function whose derivative is cosecant cotangent? Right? And the answer is not exactly, but close, right? We know that the derivative of cosecant is negative cosecant cotangent. So here's what you can do. You don't have to show this step, but notice that if I make the integral negative, then I can put a negative sign in here, and I'm just going to reorder these things. Okay, so this expression is equivalent to that one. And what's nice about this is now I know, oh, negative cosecant cotangent. That's the derivative of cosecant, right? And this negative sign is going to come along for the ride. So I'm going to get negative cosecant x plus c. Okay, so that's that one. Let's do t squared minus 2t to the 4th over t to the 4th dt. So notice that I switched up from x to t, right? So I have to have a dt instead of a dx. Okay. Well, same problem as before. This integral doesn't distribute across the division. So I've got to use some kind of algebraic manipulation. And what I'm going to do in this case is I'm going to rewrite this as t squared over t to the 4th minus 2t to the 4th over t to the 4th. Okay. T squared over t to the 4th is 1 over t squared, or in other words, t to the negative 2. 2t to the fourth divided by t to the fourth is just 2. Okay, so this didn't turn out so bad after all, right? I add 1 to the x one, I get negative 1, and then I divide it by a negative 1, and I'm going to get negative t to the negative 1, right? So it's going to be negative t to the negative 1, and then here I have a 2t to the 0. Well, that's just going to be 2t to the first power, right? So minus 2t, and then plus c. And I can call this negative 1 over t minus 2t plus c. However you prefer it is fine. Okay, one more that kind of like that. Let's do the integral of x squared over x squared plus 1 dx. Now, taking your cues from the problem that we just worked out, you might be tempted to say, oh, this is just x squared over x squared plus x squared over 1. But it doesn't work that way, right? That's not how fractions... So the reason we're able to do what we did on the previous part is because when you add fractions, you add the numerators and leave the denominator unchanged. So we just used this fact in reverse, right? We went from here to here. But it is not the case, right, that a over b plus c equals a over b plus a over c. This is not true. Okay, that is not true. So you can't do it. You can't split the denominator, right, in quite that way. So here, now I'll admit to you that, like, on this one I kind of had to look at the textbook to figure out kind of what the trick was here, because it is really tricky. But this you can think of as follows. So I can add 1 as long as I then subtract 1. Right? So in other words, if you do the subtraction, you get x squared plus 1 minus 1. That's just x squared, right, over x squared plus 1. So that works out, right? Now the beauty of that is that x squared plus 1 over x squared plus 1 is, of course, just 1. Now maybe you think that doesn't look any better from what we started on, but here, I mean, look, this is the derivative of 1 dx minus, or not the derivative, the integral of 1 dx minus the integral of 1 over x squared plus 1 dx. Well, that's just dx. Dx over x squared plus 1. So this antiderivative we can figure out pretty easily, right? Antiderivative of dx is just x. But what about this one? Can you think of a function whose derivative is 1 over x squared plus 1? So it should be tangent inverse of x. And there you go. X minus tangent inverse of x, right, plus c. Okay. So those are all the examples that I want to show you of just like straight integration. Of course, there's other things that we can kind of figure out now as a result of having this antiderivative idea. So let's suppose that f of x has the property that at each point on the graph of f, the slope of the tangent line is x squared. Now let's find f if f passes through the point 2, 1. Okay. Well, this is just a fancy way, right? When it says that f has the property that at each point on f the slope of the tangent line is x squared, the slope of the tangent line, that's just the derivative, right? This is just a fancy way of saying that f prime of x is x squared. So you know that f prime of x is x squared, and you know that f passes through the point 2, 1. So can we figure out what f is? Well, sure, right? F is just going to be the antiderivative of its derivative, right? So what's the antiderivative of x squared? You add 1 to the exponent, divide by that new number, you get f of x equals x cubed over 3. And then, of course, you have your constant value. Now, if we want to find what the function f of x is, then we would like to have a number to replace c with. And we can use this fact to do it, right? We know that the function passes through the point 2, 1. So we can say, all right, when x is 2, y is 1. So we get 1 equals 2 cubed over 3 plus c. And then solve for c, right? This is 8/3. 1 is 3/3. 3/3 minus 8/3 should be 5/3. And negative 5/3, sorry. Okay, so c is negative 5/3. That means that f of x is, I could factor out a 1/3. I mean, I don't know. But it's going to be x cubed over 3 minus 5/3. Okay, and there you go. So this kind of problem is, it's actually, it's a kind of problem that's called a differential equation. You really just solved a differential equation. There's a whole class called differential equations, right, that you would take after completing 3rd semester calculus. Or actually, I think you can take it after you complete 2nd semester calculus. And it's all about solving equations like these. You can imagine, they get a lot more complicated than this. But in a differential equations class, the problem would likely be stated kind of like this. It would say something like solve the initial value problem dy dx equals cosine x, y of 0 equals 1. So here they're giving you the initial value, okay? And then here's the differential equation. So let's see if we can solve it, right? If the derivative is cosine, then the original function should be sine, right? Derivative of sine is cosine. So we know that y equals sine x plus c, okay? Now when we plug in 0 for x, we should get 1 for y, right? So we have 1 equals sine 0 plus c. Well, sine of 0 is just 0, so we get 1 equals c. And therefore, y equals sine x plus 1. And there's the solution to that initial value problem. Okay, so that's it. That's all I wanted to say for this section.